пожарной безопасности и так дальше, который он должен пройти в соответствии с своими должностными обязанностями. От кого он пришел? Ладно, зайди. Он на самом деле его получали все, потому что пришло время сбить их. Как, блин, говоришь, как в техническом университете, если у людей совпадают имена с фамилией, не является подчеркивание 1, подчеркивание 2 и так далее. Еще раз говорю, через год вы зайдите на платформу учения и там увидите. Присылал он, что это нет, а условия как 14 лет. Не делать нечего. Вот сам прикол. Сейчас. Want to be expert. Come over. Breathe for breathe. Time. Come on. Someone else appears. Students we need more students. Students to the god of students. Okay, let's go forward. Today I would like to continue this limitation of discrete time signal processing. To show one limitation, I would like to put a light on one of the specific kind of rows. There is idea. System of function such system of function is orthogonal and may be used as a base for kind of Fourier decomposition. Let's say that we have some kind of signal where what's important, frequency is frequency range is between minus omega max, So signal with limited frequency range. I can substitute my signal with a Fourier transform at power z omega. Here, Gs is a spectral function of my signal, result of Fourier transform. Spectral function of my signal achieved with the help of Fourier transform. I perform Fourier transform and I get my signal spectral function, Js. Important, once more, my signal is a limited spectrum signal, or it occupies only limited range of frequencies. It is possible in mass sense, it is possible to do a trick. Perform a Fourier transform on spectral function, assuming double omega is some kind of period. I don't know, maybe something like this looks not S but GS. Omega max minus omega max. I can assume what this is kind of period. And perform a Fourier transform on this object. If in mass case nothing fails, I will be able to substitute my spectral function with a form of Fourier rho. From minus infinity to infinity, a power J double P divided by double omega max omega. Here's the trick. I'm attempting to substitute spectral function with rho. For this rho, this will be complex, definitely. How can I get it? One moment. I will try. Will be something like I need divide by period, so double omega max minus omega max omega maximum. Yeah. Spectral function f power J double P divided by double omega max omega, and this will be integrated in the space of frequency, so I will get 1 omega maximum frequency minus omega max omega maximum. My spectral function f power K P divided by omega maximum omega. Interesting formula. Where I started with what my signal can be represented via Fourier transform. Yeah. Power dV. Yes. If I would like and here also the omega. It's not double but omega. You see what they are familiar? But these two formulas are very close. I can write what?
This is like in how to say. First one is
Signal
signal
to its spectral function. And second one
is
components of the composition of spectral function. You know what I can do? 1 second. You'll see. I can tell what vectors or weights of this decomposition are double P divided by omega max. Signal values at point scar P divided by omega max. Rewriting in simple form. Double signal taken minus delta when delta time space is time step P divided by omega max. I can find values of Fourier decomposition of spectral function via instant values of signal. Meaning I can write my spectral function in the form spectral function of my signal will be sum from minus infinity to infinity signal values the time multiplied by a power so k delta t omega equals to sum minus infinity to infinity values of my signals at point k delta multiplied by a power minus k delta t omega. I can obtain values of spectral function since the signal will have discrete spectrum. I can obtain values of spectral function via samples of signal. Going forward, I can go forward. So I can my signal S 1 divided by double P into minus omega maximum delta t sum where k should change from minus infinity to infinity signal values delta t a power
delta T omega multiplied by e power j omega time d omega. And this can be simplified. 1 second, I will try not to miss. I will try not to miss anything, so it can be rewritten as delta time divided by p sum from minus infinity to infinity signal values at k delta time multiplied by omega max t minus k delta t divided by omega maximum t minus k delta t. Equals to this one is omega max, not something else. I hope it's correct here. And I can trust what I already corrected. So I will be able to rewrite this as divided by p somewhere from minus infinity to infinity signal values at point delta time minus omega max t minus k delta t divided by omega max t minus k delta t. 1 second, I will write it in final. Finally, I can abandon because I have delta divided by double p. Because I have 1 divided by double p in front, finally I can write it this way. Sum minus infinity to infinity signal values at k delta t multiplied by omega max times k delta time divided by omega max t delta t. The thing what I see is one of the form of Fourier law. I can use once more sine kx divided by kx, where k, let's say 0, 1, blah, blah, infinity, is a system of orthogonal functions. It can be used as a base for Fourier transform. It's a system of Fourier orthogonal function fk not t, blah, blah, blah. One interesting moment. Each of this function equals to 1 at a point k double p divided by omega maximum. And the symbol K1 divided by double F max, if you like it. So it's 1 in points double P divided by omega maximum. And it will be 0 at a moment K1 divided by, wait 1 second, double one, wait 1 moment, it will be 0 at moments m, 1 divided by 2f max, where m is an integer. M is an integer. So this means what in the points, 1 divided by f max, whole row reduced to only one member. Whole row reduced to one member, and this member will be value of function itself. There are moments where all high members of row are 0, and only value of signal at this point remains. But we do know what this row represents signal precisely. This means very important moment. F signal limited or capped with F max, it can be precisely represented if we take samples with sampling interval p divided by omega max, or 1 divided to F max. This proves Nyquist idea. Particular case with rows like sin kx divided by kx proves what Nyquist idea is correct. Because such kind of row, how to say, diminish or reduce till one particular member in some specific point. It's enough of one point to prove Nyquist idea. We can, if we take a closer look, we can see one problem. What the problem is, if our signal is non-periodic, it has unlimited, in theory, spectral function. It has, in theory, unlimited spectral. In reality, I don't know if this is cap of my, it's like to say borderline for, man, it is possible to put a limit. I can put this line with idea, what this part contains, let's say, 90, for example, 90 or 95% of whole signal energy. If so, if I, how to say, cut the tail of spectrum, in theory, spectrum is infinite. But I can put a coupling, how to say, I can put a threshold line, limiting amount of energy inside, how to say, envelope or frame. If I do so, if I abandon infinite tail, I can say well, this is my parent, and I will get what? I will get one interesting number. It will be double F max period. It's a number of reading describing my signal. Yes, I will not, I would say, there will be some inaccuracy because I ignore tailing of spectrum. But it's under control. This number of reading or number of points fully describing signal within frame of 90% of energy actually it's free coordinates for my signal. There is one how to say, underwater storm, one problem. If my signal has an interrupted spectrum, everything fine. But if it's truly it's for non-periodic, okay. But if it's periodic, it will have discrete spectrum. And my measurements, my points of measurement in frequency space can hit these points of spectrum and cannot. Understand? If I have spectral lines and my measurement points are between them, I will get some kind of distortion. I need, it's a problem, but I need synchronized measurements. If I would like to play this game with periodic signal, I need to synchronize measurements. So my points in frequency space should be where the signal spectrum has values. Or I can try between, I will get some measurement, but I will get, in reality, I will get some stupid interpolation. But to get precise results, I need to synchronize. I need to, let's say, I need to adjust sampling frequency with something like parallel to get in points where my periodic signal spectrum has values. Understand? If I simply take measurements where I need, there will be offset between points where my signal has values in frequency space and my measured points in where it will happen. Decompression of something like decompression of Ampere signals. It will hit me. To avoid this, I need to synchronize frequency lines, like on ruler. Rulers and points, 1 centimeter, 2 centimeters. They should correspond to K double P divided by periods, points where my signal spectrum has values. I need to measure in spectrum lines. Or I will get some stupid. Okay, let's take a look bit deeper. I forgot to change course. Let's say I have signal with limited spectrum. So I have omega null, omega max, double omega max by half, and delta omega and delta omega is much lesser and central frequency omega 0. Okay, even more. I can relax. Let's say I have frequencies from omega maximum at my omega 0 is omega maximum omega minimum by half, and delta omega so delta omega is much less and omega 0. Even though non-symmetric spectrum, but width of the spectrum is much less than the central frequency of spectrum. I will see non-zero values of spectral function so will be not zero only in space from omega max. Only somewhere in between. Right? But that's not all. What do we know about spectrum function? What it's symmetric? Here we have GS from omega, and this part is conjugated. Always. Spectral function always has its mirror part in negative frequencies because of Euler's formula. That means what there will be and one more, how to say, branch from minus omega minus omega minimum. How to say, mirror of the main, mirror of the positive, or mirror, call it this one. Not mirror, but mirror. I can say what my common spectral function is a sum of two parts. Let's say, but not GS, it was uno. So go. Let's say it has two parts. 1 and 2. 1 for negative, 1 for positive. Some I don't know. This one for positive frequency is number 1 and its mirrored part. This one is complex and this one is conjugated. We can say what is a second part, second spectral function. This one from omega main to omega max, and here minus omega minimum, and this point is minus omega maximum. One second, I will. Oh, here is my frequencies. I don't know. Okay, this is my first one. This is my second. And they are, how to say, mirror, they are conjugate. What can I do? matching this original. It's kind of periodic, bit of periodic function, yeah? Especially if I draw modulus. I can do whoop, 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 whoop. I can create a periodic function matching my original where it exists. It will be with spirit double delta omega, with period double delta omega equals to double omega 0 divided by n capital where n capital here I need max from integer of double omega 0 divided by delta omega. Just take max even integer from this division and you will get correct spacing to create such periodic function. My green line is some kind of function. I will call it GP, P from periodic. It's a periodic function. It has a period double delta omega. I can represent it with a Fourier rule. I can substitute my periodic function with Fourier rho. And its Fourier rho will be something like this. So my green periodic function can be written as 1/2 somewhere from minus infinity to infinity a power jk double p divided double delta omega, and here should be frequency. Now, where am I? I can apply this rho to get my original signal. It will be 1 divided by double p minus omega minus omega height. This is max, this is min. Periodic function a power dot omega time d omega plus 1 divided by double p omega minimum omega maximum. My periodic function a power dot omega time d omega. if I substitute this periodic with it Fourier representation and perform all the integration work, I will get, I hope I copied it correctly, something like this will be sum stop minus infinity to infinity values of my signals at point K double P double delta omega, elements of the row, so it will be sine of delta omega by half multiplied by minus k double P divided by double delta omega. Here will be delta omega divided by k double P double delta omega, and this should be multiplied by cosine of omega 0 minus k double P divided by double delta omega. Oh. Woo. Nice formula, isn't it? It's nice formula, but take a closer look. This one is null. It's only set of values depending on network or frequency scale. This part also null. The only unknown is this part. Actually, it's the only variable. Other are constants. Other are just constant. Actually, it's kind of frequency scale. And here we can fastly conclude what this kind of signal with limited frequency range is in reality fully described by its values taken with the sampling, sampling points at double P divided by double delta omega. Take the sampling point and everything should be fine. With one, there always is something but. And here is one problem. Let's say, okay, you have delta omega, omega max minus omega min. Fine. But if you can say what omega 0 divided by delta omega is integer, you will see what our spacing delta omega small equals to frequency range. And our samples will be where? Will be at double P divided by double delta omega, or at a space 1 divided by double delta F. So it will be like signal in frequency range from 0 to delta omega. We need discretization frequency double delta omega. And our sampling frequency should be exactly double delta omega. Exactly. If you take double P divided by discretization frequency greater than double delta omega, this will lead to one serious problem. What kind of problem? In your frequency range from omega min to omega max, there always be some how to say, there always will be so-called damaged or critical frequency. Being, how to say, integer multiplied by omega omega of discretization equal to double P divided by your discretization sampling. And this one will disappear. It will create a blind spot. That's not one frequency. In reality, you will get cupola-like area, how to say, damaged. It will be blind area, not reflected. To solve this, special measure should be taken. To prevent it, 1 second, I will do tiny service to my instrument.
Wait, next week I will not come. Next week is 12:30, so I'm not coming. But the next time we have like 10 a.m. I'm not coming, and if I don't come and no one else comes, it's going to report to international patrol. And then we said those look at it, it's only 12 friends that come the whole time. I think Fleming has this course. Fleming.
What?
Fleming.
Uh-huh.
She has this course,
Yes.
but I've never seen her in this class. Oh,
And even this Turkish guy.
he has this one?
Yes. Yeah, I think so. Was really. These guys are fucking crazy.
That comes like once in 2 weeks. And then the Turkish girl, she comes like once in 2 weeks. Oh, next time I'm not gonna call. And they'll send an email.
You came from Akropol.
So yes, please.
So where am I? I would. We saw what discrete time representation of limited frequency signal may have blind spots. May have blind spots. To prevent its negative influence, there is one trick. Because these two spectral functions, G1 and are conjugated, they are mirrors one of another. I can do different trick. I can decompose my function in 1 second. In one, hey, what I'm doing? No. This not. What can I do? I can say what my signal is 1 divided by double P minus omega max minus omega minimum. Here it's conjugated. Omega a power dot omega the omega plus omega mean omega max same one from omega but not conjugated a power dot omega the omega. I can write in this form. This function can be, this spectral function can be assumed periodic and decomposed into Fourier rule, assuming period, kind of what period is delta omega. Omega max minus omega minimum. This rule this will be true only in frequency range from omega min, omega max. We need to keep it in mind. But that's not a huge disaster, because anyway we cut to avoid everything, anyway we cut upper frequencies. It's not a disaster. So I will be able to do something like this. I can substitute my signal with two parts. One, double P delta omega sine of delta omega by half time minus k delta omega. Stop. No, I can do like this. I will get nonsense. I can do like this. And here will be delta omega by half multiplied by e minus k double P delta omega. Yes, this is correct. Multiplied by cosine of omega 0 minus k double P divided by delta omega minus, I will, this part is for complex. Now I will write the second part. This part is the composition corresponding to the complex or positive. This part is for positive frequencies.
Now for its conjugate.
We have 1, 2. This one positive. This one is conjugate mirror. This part is dancing from positive frequency. Now the second one. The second one will be minus sum, that from minus infinity to infinity. Conjugation of my signal. It's a conjugated signal. What's a conjugated signal? If my original signal can be represented with some CK minus JSK, conjugated one is for CK plus JSK. That's it?
So the opposite.
It's mirror. Not opposite, but mirror. There is, for many signal, you just need to impose phase shift. Signal and its delayed replica. So it's conjugated. Double P divided by delta omega sine delta omega by half k minus divided by delta omega divided by delta omega by half K square double P divided by delta omega multiplied by sine of omega 0 square double P divided by delta omega. Here it is. This second part, relying on conjugated signal, do not have or is immune to blind spot problem. Actually, we will speak on Hilbert transform.
After the break.
Wait, after the break, first I would like to speak on time frame limitation. We will speak on Hilbert transform later. This idea actually to dance with this nice formula, we need to know how to say Hilbert transform allows us to do one trick. If we have some kind of signal, in any moment we can represent it as a value of some vector with angle in this time and the magnitude as a function of time. Any point can be assumed as a end of some kind of vector on complex plane. I will speak.
You mean in polar form?
Yeah, it's easier to represent it in polar coordinates, but it's not. It can be on complex plane. So it's kind of shifting vector equals to our signal. I don't need genre. I need
How did time change?
yeah, I see what I'm thinking. Next one, I would like to first point on the limitation of time window. I'm just thinking where should we start? In 12/3 or earlier? I don't know, maybe someone arrives.
Professor, can I ask you?
Yeah.
It's not actually related to our topic, but I have my personal question.
Yeah.
In our course, in our electronics course, do we have any other subjects except